Okay, well, it's my pleasure to introduce Niels Kuster, who heads the major laboratory for testing of cell phones and other related devices and some additional experiments beside in Switzerland. And he'll go ahead and give us some more data on radiation dosimetry.
Thank you very much. Thank you, Deborah, to invite me to this important meeting. I noted last night that she changed my title of the presentation. I was supposed about talking about children exposure, and the title has been changed to a less interesting topic. Probably mainly because she wanted to avoid that we're going into a dog-cat fight with Ohm on the subject, which we have quite a history on. And she is right that we should avoid this here because we deviate in some details. But one important conclusion, which is important for this meeting, is that we both agree that children's brain cortex is higher exposed than in adults in average by using mobile phones. So I would talk about a dumb topic about reliability of dosimetry, talk about units of dosimetry, procedure to achieve reliable dosimetry, progress in dosimetric tools, and then I will add some juice talking about mobile phones, base station, bioexperiments, and exposure assessment in epidemiology, and conclusions. So this is a MR example just to show you that you have a uniform B-field exposure, and what you end up is with a very non-uniform exposure of the tissues. See, the tissue exposure for these uniform fields vary by a factor of more than 100, even factor of 1,000. And it's, as you see here, they are shown different anatomies, slightly different posture, lying in an MR machine, and you see the exposure is completely different. So we have a strong dependence on anatomy, and the incident field does not tell us anything about the exposure. In exposure units, Ohm already discussed it a little bit. So we have cardiovascular hazards, for which whole body exposure, which is a measure for how much energy is absorbed in the whole body, but it only increases the temperature. It's only a good measure for cardiovascular hazard. Then we have local heating as a possible hazard, which you can limit by limiting the local absorbed energy. And then what we talk here mainly is non-thermal effects, and now these are more complicated, depends on locally induced fields, E and H field, in time domain, so we are not sure which units we have to look at. But very little has been done in this field. So we have the SAR we were talking about, which is a specific absorption rate, whole body SAR, which is the total absorbed energy rate divided by body mass. Then we have the peak spatial SAR over 1 gram or 10 gram. Now, cardiovascular hazards are limited in the safety standard by limiting the whole body SAR. Local heating is limited by limiting the peak spatial SAR. And for non-thermal effect, if they exist, we do not have a real unit to consider, and it's not considered in any safety standard, except that SAR is a good surrogate for time averaged E square. But definitely we will have, for non-thermal effect, a strong tissue dependence. It's obvious that brain tissue might act differently to fields than fat tissue. E is the electric field, H is the magnetic field, I'm sorry. Non-thermal effect in the investigation would require a paradigm change in the units we look at. So the question is now how reliably we can assess whole body SAR, peak spatial SAR, or the distribution of the electric and magnetic field, which would have to characterize in terms of amplitude, frequency, modulation, intermittency, if we want to assess the the parameters we are considering or discussing currently in non-thermal effects. So how do we obtain dosimetry? We would like to use ideal tools. In measurement, that we would like to instantly measure all information in time domain, and with very small uncertainty. Numerically tools, we would like to automatic segmentation of the real world and then instant 3D solution in time domain, and very good absolute uncertainty. We do not have and will never have these ideal tools. Measurement tools, for example, are good for real world. They have absolute uncertainty, is known. However, the sensor size will always be finite, and we can only apply it in free space phantoms and cadavers because it would be invasive. Simulation tools have almost unlimited resolution anywhere, full time domain information, but they apply for a simplified world, for a segmented world. So they only provide relative known uncertainty. So a reliable dosimetry will rely on analysis of the complex environment by simulation. These simulations have to be anchored to the real world by measurements, and then an assessment of the uncertainty variation is always necessary. Therefore, for reliable dosimetry, we always need simulation and measurement. So what do we need to do reliable dosimetry? We need human models representing user population with respect to anatomy. We need to model well the sources. We need the appropriate simulation tool. Then conduct the required number of permutation to represent the human population, validate it, and determine the variation analysis. What kind of tools we have? There has been considerable progress being done in this area. We developed the virtual family together with FDA, which are MRI-based, high-resolution 3D surface models. The Germans financed the extension to the virtual classroom with a lot of different children. Then we added obese person, especially in MR. Obese have a significantly higher exposure than not obese persons. And we also developed pregnant model to look at exposure of fetus, which is also a topic which has long underestimated, not looked at in the past. RF exposure is very relevant to the posture of the human models. So we developed software in which we can pose the human models. All these models can be posed without changing the volume of the tissue and without losing connectivity of the different tissues. You can even go farther, look at the functional subregions of brain. So we implemented the Thalrach transformation into the software, so we can look at functional subregions of different brain regions. I didn't want it to jump to here, but we're now at the measurement tools. So the research started in the 70s. So at the beginning, this was measurable. So with this was the first implantable probe, but it has a performance which is not satisfying today. There's an isotropic response which is too large, and also the sensitivity and dynamic range is not sufficient for today's dosimetry. So improved tools has been developed for much smaller probes, which better performance for measuring in tissue, for measuring the electric near field or the magnetic near field, as well as temperature sensors.
These probes are in cadavers or in the models?
These probes are used, they would be invasive to use, so they are used in artificial phantoms or cadavers.